All right, so this is Accelerating Life Sciences Research with High Performance Computing on AWS. And today we're going to look at an overview of the AWS infrastructure, take a look at the solution components for HPC, and look at some of the common use cases for HPC in the life sciences and common tools that are utilized, and look at some specific use cases and customer success stories for HPC in the life sciences, and hopefully follow up with some best practices and then resources for getting started. So first, an introduction to the AWS Global Infrastructure. Right now, the AWS has 18 public regions, and which represent a total of 55 availability zones, and one local region around the world. And we are looking at, or already announced plans to expand in 4 more regions, one in the US, one in Sweden, Bahrain, and then an additional region in China. And with this global infrastructure, you can access the full power of everything that AWS has to offer, including a lot of the high-powered, high-performance compute resources that we have, which I'll describe in a little bit. The interconnect between these regions is used, not just the public internet, but the Amazon Global Network as well. So the Amazon Global Network is a redundant 100 gig network that runs between all of our regions, and then even in a redundant capacity between a number of our regions, and provides private capacity between all regions except for the regions located in China. Now, to take a look at high performance computing on AWS, we look at some of the benefits for high performance computing on AWS. Using the cloud, and you can innovate faster with virtually unlimited infrastructure that enables scaling and an agility that you can't attain on premise. And we're going to review how some people do that with high performance computing in just a little bit. You can also optimize the cost that you utilize. There's a tremendous cost savings to be had when deploying high performance compute resources in AWS versus something on premise, because and for a number of factors, but primarily AWS is a utility-based model. And so you only pay for what you consume, whether that be compute resources or storage resources or what have you. So you're able to get a far better return on the investment that you make, because you are only paying for what you consume when you consume it. And then the cloud is a good meet in the middle kind of place. And so it allows for increased collaboration and secure access to all the resources that you deploy around the world. And for the different work types that are common in high performance computing, from tightly coupled parallel computing all the way to high performance data storage and analytics, AWS provides a number of features and advantages for enabling these different workloads in the cloud. Scale is the primary advantage. You can reach just about any scale that you want or need by taking advantage of compute resources in the cloud. You have a wide variety of choice and a wide variety of things to choose from in the cloud in terms of resources, and we'll describe those in a moment. And based on those choices, you can reach just about any performance profile that you are required to reach. So if it is accelerated computing with GPUs, there are resources available for that. And if it is massively parallel workload that gets deployed, loosely coupled parallel computing as listed here, we have the ability for you to reach any performance profile you need at just about any scale. Some of the components that go into high performance computing are listed here. And the core of that is really the compute listed in the center. And that is our EC2 instance fleet, which has a number of features underneath it, including accelerated platforms and specific features around that, which I'll get to in just a moment. We have spot pricing available across all of the instances in the fleet. and then the ability for you to scale to any degree that you need using auto scaling, which is a default feature of EC2. In addition to that, we have a number of tools that can be utilized to instrument your workflows and workloads on AWS, including automation and orchestration tools like AWS Batch, storage platforms that can be utilized to deliver data to your workloads and applications and receive data in return, such as the Elastic Block Store, Elastic File System, and S3. Networking connectivity that provides not just basic networking functionality, but also enhanced networking and the ability to group together EC2 instances into placement groups. And then extended application level components such as DCV and AppStream that allow for give excellent visualization capabilities to resources that are remote from the cloud. Expanding a little bit on the instance suite that's available, the spectrum describes the full range of instances that are currently available on AWS. And it encompasses everything from general purpose instances like the T2 series, all the way to bare metal instances that are now offered on EC2. In between, there's a number of interesting ones, but for high performance computing, we see that, you know, there are a few that are compute optimized that have a higher core count within them that are well leveraged for good distributed workloads or massively parallel workloads, all the way to ones that are memory optimized, which can be useful for large analytics workflows and large workflows that operate on a significant amount of data. Graphics intensive instances which provide, and GPU compute instances which can provide significant graphics capability or GPU assisted accelerated computing capabilities. And now even the F1 instances which provide FPGAs along with a compute platform. So the ability to build your own or pull in partner provided images into the FPGA for specific or very customized computing tasks. Expanding on storage a little bit, there are a number of different storage platforms that AWS offers, from everything from file-based storage, block-based storage, to complete object-based storage. And you know, in each of these families, there's at least one, usually two offerings for some of these different things. So file-based storage, we have the Elastic File System, the Elastic File Store. For block, we have the Elastic Block Store, which can attach to any instance that is deployed in EC2. There is also the instance store that is coincident with the instance itself that can be utilized for different compute and data transfer tasks. Object storage such as S3 and S3 infrequent access, along with cold storage platforms, cold storage object platforms like Amazon Glacier. Now, specifically for high performance computing on AWS, we offer, you know, the ability to create secure and well optimized HPC clusters. And you can bring them up and tear them down in just minutes. And that's the really exciting thing about doing high performance computing on AWS. It's that it's no longer a fixed resource which has to be managed as a single unit, and you know, everything has to be kind of serialized and prioritized through it. Any number of clusters can be created for any number of customers and customized and tailored to specific workload requirements as they're created. And when doing so, we see people take advantage of a number of the different services that are available on AWS in different combinations. So for HPC workloads that require a significant amount of graphics representation or rendering, we have the ability to do that with 3D graphics workstations set up on the instances I described earlier. We also have the ability to take advantage of auto scaling within EC2 to create any size HPC cluster that is necessary or needed, and interoperate with the different storage options I described. And we can do this and connect the entire instance or VPC that is up in the AWS to your on-prem resources right now, and then have a number of facilities in place to transfer your data between AWS and your existing on-prem resources. So Direct Connect gives the ability to directly connect your data center with an AWS region and transfer things over that direct connection. But there are also bulk storage options, bulk transfer options like Snowball that can be used to transfer a significant amount of data in a very small amount of time. Now, taking a look at high performance computing on AWS for life science applications and some of the common tools and partner tools that are available, it's first helpful to take a look at the problem space for high performance computing. And represented here are some of the common problems in high performance problem categories in high performance computing. In the upper left quadrant, you have tightly coupled, highly, but very data light, don't take a significant amount of input data relative to some of the other workloads, but generate a significant amount of data. All the way to the bottom right, which represents a lot of the massively parallel workloads that are very data heavy, taking a significant amount of data, and but almost not coupled at all between their processes. Highlighted are a few of the use cases that we have in the life sciences and some of the things that I'll review today. So in a more coupled sense, we have, or in a data heavy sense, I should say, we have things like molecular modeling, all the way to more tightly coupled things like clinical trial simulations, and then massively parallel workloads like genomics. Looking at some of the common AWS tools and resources that are available in the life sciences, we have multiple clusters, the ability to create more than one footprint in the cloud. And we'll review CFN cluster, AWS batch, and step functions. So being able to deploy multiple high performance compute clusters is really key. Whereas older high performance compute resources were tailor-made for a specific purpose and then made to fit the widest range of workloads possible for that specific industry or customer. The ability to create any number of high performance compute clusters at any time is a really powerful advantage that people do take definite advantage of in the cloud. And the beauty of it is that they can be deployed at the same time. There is no limit on terms of resources that people can consume in AWS. And so if there is some, where a lot of existing on-prem HPC compute resources would have to take advantage of complex schedulers or queue management systems that would arbitrate access between different users for the same set of resources, that is no longer necessary on HPC clusters that are deployed in AWS, because you're able to deploy any number of customized ones at any time. And to do that deployment and automate that deployment, there are several common tools that are provided, and AWS provides CFN cluster as an example. Now, CFN cluster, the CFN part stands for CloudFormation, and utilizes CloudFormation to actually deploy a complete HPC cluster on AWS, and provides that cluster, once deployed, gives a pretty standard HPC environment, access to schedulers for jobs that are already written to take advantage of a scheduler, a shared storage environment, and an MPI environment as well. There are several other small utilities that are also provided to assist with compilation and actual job execution. AWS Batch is a service that has been deployed on AWS to provide dynamically provisioned resources and takes care of all the planning, scheduling, and execution for batch jobs, for common batch jobs, and doesn't require any batch software to install. The nice part about AWS Batch is that it gives you the ability to focus on just on your applications and the results that you want, and not have to worry about implementing a batch system again and again for some type, for operation in the cloud. And in a little while, we'll see how AWS Batch is leveraged in some of these common workloads in the life sciences. But in a general sense, this is meant to describe the actual batch execution framework for just a common, any type of job that goes in there. And so it's able to pull data from S3 to respond to trigger and events from S3 and actually build a queue of running jobs and take care of actually the execution for those jobs in their different compute environments and manage the output from each job into its proper location. AWS Step Functions goes a step further and makes it easy to coordinate the components of a distributed application using visual workflows. And so it is a good way to define and visualize in the console here a nice way to see how the job should execute, especially given different conditions that are placed during the job execution cycle, and then monitor the actual execution of the job as it goes. And so sometimes even over the span of days or longer, you can visualize and visually see the progress of a job as it travels through step functions. And to manage the different states that step function provides, it has a number of different tasks that are available for users to customize and deploy. And so everything from simple success or failure to wait states to what should be parallelized and to actual branching logic can be defined within step functions and leveraged for complex workflows that will travel through multiple states as they progress. And again, in a little bit, we'll see how this is applied in some of the work areas that are utilized in the life sciences. And not to go unnoticed, but there is a significant partner presence in the AWS Marketplace that provide a number of good utilities and common tools for high performance computing. And so Alsace Flight is one good example, shown here providing the IGV genome browser, but it has a number of other utilities available as well. And so the image is available in the Marketplace. Taking a specific look at some of the applications and tools and a few of the customer success stories for high performance computing in the life sciences. First one up is collaborative research environments. So this is an interesting space. The ability to build multiple clusters often leaves people with the sense that they're going to kind of splinter off and go into their separate little areas and just do some computing on their own. But the beauty of AWS and one of the things that it provides best is the ability to draw researchers together into a common environment and utilize a common framework and compute environment for all their work. And especially with data-heavy workloads, such as genomics and things, where you are either faced with the option of transferring a significant amount of data around and then trying to manage that data and the integrity of that data as it transfers, versus collecting and consolidating it into a single place and providing people with the ability to draw from that single place and deploy as many customized high performance compute clusters as they need, which draw from that common location. It has been a tremendous advantage for the industry and something that's been utilized very heavily. And there are a number of different collaboration models that are available. Everything from spanning multiple AWS accounts to operating within one account and utilizing the management tools that are available. The nice thing is that the management tools are consistent no matter which model is chosen. And for the life sciences, there's a number of significant amount of data that's pulled in from things like contract research organizations, CROs, university collaborations or university collaborative efforts with universities, along with the vendor that is sometimes sponsoring a lot of the work. And being able to create these structures in AWS gives them a place to do all this work in a common area without having to merge and manage all the data that comes in and out of such a collaboration. And a customer that's done tremendous work in this area is Celgene. And they had a number of HPC workloads that needed to be consolidated on AWS of all different types and varieties. But we're primarily looking to store a couple hundred terabytes of genomic data for a number of studies that were taking place. And using AWS and using the different tools provided, they were able to build a system that allowed for this collaborative research environment to be created and invite researchers, CROs, university collaborators, and things to take advantage of this common environment and access this data and take a look at the tools that had been provided for that analysis and run them and evaluate them in their own specific context while operating on common data. Baylor College of Medicine has also been able to take advantage of this by creating a number of projects. The Charge project listed here is just one of a few that they've been able to create, but where they were able to invite several hundred collaborators at a number of different institutions to operate on a common set of data that was set aside. And that data set kept growing by about a petabyte a month, and it was all genomic sequencing data. And by doing this and forming this common pool of data and common pool of resources that they were able to take advantage of, and eliminating the need to transfer subsets of data around or wait for that transfer or manage the output of results or tracking who had done what. By using a collaborative research model on AWS, they were able to complete their analysis about 5 times faster than they would have been able to do on premise. Specifically in genomics, this describes the typical workflow in genomic analysis. And it's a massively parallel workflow that's pretty well serialized through a number of different stages. So you have sequence data that comes in in a sort of random, disconnected format. It needs to be aligned to a particular reference. Then that reference needs to be, then that aligned read needs to be called out for different variants within that data, and then description of those variants is generally provided afterwards. And using some of the tools I described above, you can create a very nice, very smooth running workflow for genomics and deploy an easy architecture for genomics on AWS. The tool described here uses both AWS Batch and AWS Step Functions to provide that functionality. Now, it is using a number of containers which contain the specific tools utilized for the different aspects of that genomics pipeline that's described above, draws its data in from S3, takes care of orchestrating the batch jobs that need to get executed for every sample that's run through. It does that primarily through launching Lambda functions, and then drives AWS Step Functions to make the decisions about the state of the individual workflow. And so when things like quality stats are pulled out and they don't appear to be very good, or what have you, different decisions can be made at that point as to the downstream impact of that on the workflow overall and how the data is described and annotated later on. And this kind of setup is commonly used. One of the labs that contributes a significant amount of work here is the Berkeley AMP Lab. And it's a multidisciplinary effort from the University of California, Berkeley, that aims to apply a number of different scalable analysis and has a particular focus on machine learning in genomics. And they've been able to really utilize AWS because it gives them an access to a number of very high performance, high capability resources very quickly. And so, as noted here by Michael Franklin, they were able to solve a lot of real world problems because of the resources that AWS gives them access to. A particular interest here in the genomics community is the ability to take advantage of accelerated compute options. So you have Edico Genome, which has produced the Dragon, a genome pipeline that can be deployed on FPGA instance, and specifically the F1 instance that Amazon Web Services makes available. And using the Dragon and the accelerated compute pipeline that it provides, they're able to, Edico is the current world record holder for the speed with which a number of genomes have been processed. And this particular record is against 1,000 pediatric genomes, which were processed in just about 2 hours and 25 minutes. Another area is clinical trial simulations. So Bristol-Myers Squibb runs a significant amount of their clinical trial simulations on AWS. And these are something that they've been able to reduce by, well, more than about a factor of 60 by being able to take things down to just a little bit over an hour on AWS. And the nice part about it is that by doing so and by using the platform to develop higher sensitivity, higher accuracy analytics, they can reduce the number of subjects that are needed in any clinical study by about 1/3, and then the number of samples that are required from every subject by almost half. And this helps them achieve faster time to results, but it also gives them the ability to more preciously use a lot of the resources they have. Gathering clinical trial subjects can be challenging. And of course, doing all the sampling work for all those clinical trial subjects can be very, very challenging as well. And so by being able to take advantage of a lot of the high performance compute resources that are available in AWS, they can more finely tune their clinical trial studies to get not only faster results, but more accurate results with a smaller sample size. Metadata is another AWS customer and partner that is able to innovate with clinical trial studies and on AWS, and allows them to, as they say, push forward-thinking solutions to their customers. But they molecular modeling and computational chemistry is a very fascinating process. Typically, this was actually one of the largest use areas for high performance computing in the life sciences. And so traditional pharma organizations would spend a significant amount of money on on-premise compute resources, high performance compute resources, to run computational chemistry code. And CompChem is really focused around just determining the properties of different molecules and solids. And the interesting thing about it is that that space, or the property space, varies pretty widely over the different HPC calculation space. So that quadrant diagram that was listed above. And it ranges from everything from massively parallel to really tightly coupled simulations that need to take place. And what is very interesting is that since this is been a long time interest of a number of the industries and been a long time focus of a number of different pharmaceuticals, that there are a significant number of standard solutions available, and most of those standard solutions are available on AWS. One of them is, or the most common solution that's utilized and sort of premier solution in this space is Schrödinger, which uses AWS to run a number of their different simulation products. And the performance increase that they've seen, along with the ability to scale, really gives them the ability to respond, quickly and evaluate new compound ideas very quickly. And they have begun taking advantage of things like the Amazon EC2 P3 instance, which offers GPUs, high performance GPUs, as a platform for their simulation activity. Pfizer is one of the large pharmaceutical organizations that's been able to take advantage of this large-scale data analysis and do a significant amount of work, not just in computational chemistry and molecular modeling, but in a number of different aspects of scientific exploration. And they've been able to do so and answer a lot of deep scientific questions quickly, timely, and a very scalable manner. High throughput screening. Virtual high throughput screening is always a long area, always a significant area of interest for a number of customers in the life sciences. As new therapeutics and as a significant part of in silico drug design, there is a need, of course, to evaluate a large number of compounds against different targets that have been developed. And so frequently you'll see the consumption of a large number of compound databases that have been built. And this is a really common use case on AWS and a common use case for high performance compute resources on AWS. And specifically, Novartis has taken major advantage of this. And they have been able to reduce, evaluate about 10 million compounds against a new model that they had developed. And they planned out the actual on-prem need or compute need for that activity or that program. And it came to about 40 million for them to build on-prem, but they were able to do the same thing for just about $4,200. And in spite of saying Novartis used AWS for HPC computational chemistry, it was primarily a high throughput screening job. And another new area that has emerged recently is deep learning. AWS offers a pretty wide and deep machine learning, deep learning stack. At the bottom listed here are the frameworks and infrastructure that is supported. For quite some time, AWS has wrapped this together into a deep learning machine image called the AWS Deep Learning AMI. And it's able to take advantage, it packages up a number of frameworks and tools so that to take advantage of a number of the native capabilities of AWS, from the GPU accelerated options that are available to newer mobile options like the AWS Greengrass. On top of that are platform services, which are sort of a composite of a number of other services offered, other frameworks and things, but then developed into specific services around different use cases. And so SageMaker is one of the kind of primary platform services in the AI/ML stack right now that gives people the ability to execute, build models for different AI/ML jobs. On top of those are a number of application services for vision, speech, language, and other emerging areas that are always coming online. And we've had a few places take advantage of a lot of the services that are offered. One of them is Matrix Analytics, which is able to do early cancer detection using deep learning on AWS. And the interesting thing about it is that they're able to determine things or detect cancer at a level that was previously very hard to ascertain given existing imagery and diagnostic techniques. And so by applying good deep learning solutions using, and in this case, TensorFlow on AWS, they were able to detect things at a sensitivity that they weren't able to detect before. But also, there's been a significant amount of work done to model different conditions, including what's needed for heart disease. And HeartFlow has been instrumental in creating a personalized medical technology that uses deep learning to help diagnose heart disease. And so it's really a direct application of a lot of earlier fluid dynamic solutions and things, but specifically toward applied toward the personalized imagery that has been developed for each patient to take a look at the different flow characteristics within a patient and determine different risks and risk areas for heart disease as it emerges. And right now, they're beginning to explore some of the new instances that are being offered, such as the G3, and to really instrument that work. And lastly, kind of taking a look at some of the other interesting areas used for deep learning is cardiac visualization. And so this is taking a look at the actual operation of someone's heart based on MRI images that have been taken, and to look and build a seamless visual model of the heart in action, and something that can be kind of highlighted, outlined, annotated for medical practitioners, which is something that used to take days or weeks and was very custom activity built for only very patients with very specific issues or problems, and now can be spread more widely and built more quickly to using the resources that AWS makes available and that Arteris has built. So overall, this work that has been completed, we wanted to offer some lessons learned and best practices. Very broadly speaking, we want to make sure that with any workload that's deployed onto AWS, and a lot of the HPC specific workloads in particular, want to do a deep dive into those workloads and understand a lot of their characteristics, both in terms of how they are structured and how they are run, so that we can plan accordingly, or we can help you plan accordingly. The idea being that traditionally, working with on-prem resources has required people to really just make some compromises or tailor their existing workloads to fit that single on-prem resource. But now, without that constraint, or having that constraint removed, by being able to customize your HPC cluster deployment on AWS, we can remove a lot of those earlier compromises or constraints, so that better advantage can be taken of some of the higher performance and specific resources available. When doing that, you want to make sure to look carefully into the I/O storage architecture that's used. A lot of existing workloads and jobs for high performance computing in any area, but in life sciences in particular, use a lot of traditional storage methods that have a certain number of built-in expectations. And so it's good to always take a deep dive into the I/O storage architecture and apply the architecture that best fits the job. We also want to look at innovative ways that we can bring in new options that weren't previously available, such as the FPGA and the work described with Edico Genome as an example, but also different GPUs that can be brought and GPU-based codes that can be brought in to optimize the workloads as they're moved to AWS. A lot of accelerated options while they were available, they were only available sort of intermittently for various on-prem solutions. And AWS gives you the ability to access these things at any time for any workload. And then wherever possible, make sure to engage partner solutions or rope in partner solutions. There have been a number of existing partners and ISVs that have written and produced a good number of comprehensive solutions in this space, and we should make sure to leverage them. They are more frequently than not, they are partners of AWS and work with us very closely to optimize their solutions for the architecture and the resources available. And where to get more information? Listed here is just a set of resources that you can use to take a look at some of the different options and use cases that we have in place. We do a lot of work to illustrate how certain workflows can be moved to AWS very quickly, and try to produce some white papers and other content around larger workloads and requirements in the space, including security and compliance, but also everything from preclinical research to genomics is something that we'd like to make sure we provide a good enough information on. And that's it.